Hi, everyone. I'm John McCutchan.
I'm Todd Turnidge.
And we work on Observatory together. So Observatory is a web application that's hosted by the VM. It provides a suite of program inspection and analysis tools. Everyone on the Dart VM team uses Observatory almost every day, so we're extremely committed to making this tool really powerful. And every time you come to us with a performance problem, the first thing we do is we look inside of Observatory. For those of you who don't know, Observatory is written in Polymer and in Dart.
Yeah, and a little bit of an agenda for our talk. John's going to give a demo of how he uses Observatory. I'm going to demo some of the new debugger features in Observatory. Then we'll go on to talk in general about the tool.
All right, so I'm going to demo something that I do on a regular basis on my day job, which is stare at Box2D performance in Observatory.
So what's Box2D?
So Box2D is a physics engine that there's benchmarks built around it that everyone likes to compare the performance of different VMs and runtimes. So it's really important that the Dart VM runs Box2D well.
Let's increase the font size a bit, or if it doesn't matter.
Actually, yeah, it's mostly visual. So.
OK.
All right, so the first thing I'm going to do is I'm just going to click on one of the tests, and this is just a simple blob test program. And now I'm going to connect to Observatory. So in the past, we had Observatory baked into DevTools, but we found that kind of cramped Observatory style because Observatory likes to have lots of links and browser-like navigation. So now we just print a link in the console that takes you to Observatory for this demo. Now, the main page in Observatory lists the isolates, and we can see that we have one isolate. It's called blob test, which is the program that we're running in the other tab. So if I click on the blob test isolate, it takes us to the main page for the isolate, where we can see information about recent execution history, links to various tools that are built into Observatory, information about the heap. What I'm going to do next is go to the root library for this isolate, and this is the library that contains the main function. So when we're looking at a library page, we see the other libraries that this library is imported, the scripts inside of it, the classes contain, and functions contain. Now, all of these are just regular hyperlinks that you can open up in new tabs and browse around and even share. So why don't I start with the blob test class? So now we're looking at a classes page. And I'm going to go up here and click refresh coverage. So this class has 3 functions. Here's some information about instances that we'll get to. But let's just take a look at code coverage. So
what's the green mean?
So the green means that this is an executable line that has executed.
OK.
And if there's no color next to it, the line is not executable. You can see this is just a closing brace. There's no statement on this line.
Yeah.
So if we scan through this class, we can see that actually every single line in this class is executed, which makes sense because this just sets up the demo, which is already running. But why don't we try and find some code that hasn't executed so we can see what that looks like? So what I'm going to do is I'm going to click on this, and this is showing runtime type feedback for this line of code. So this method invocation of new polygon shape, we actually see that it's of this class, and this is the class's constructor. So why don't I click over to the polygon shape class, and we'll take a look. Now, we're on the polygon shape class, and I'm trying to find some code that hasn't executed so we can see what that looks like in Observatory. So I scroll down, we see some green, here's some red, more red. So the red is these lines are executable, but they haven't executed yet. Here's this function, set as edge, which hasn't executed yet. Why don't we actually, while the program is still running, just execute it and see what happens. So to do that, I'm going to go up here, and I'm going to find instances of the polygon shape class.
So these are the strongly reachable instances of polygon shape?
Yeah, these are instances inside your program's heap that are still alive of this class. So I'll just command-click and open up a new tab. And now we're actually looking at a specific instance of the polygon shape. Now, I could just go down here in this line and start typing regular Dart code. So I'll just try and execute this set as edge function. OK, so that function ran, and it returned null, which is what we expect. Now let's go back over here. And we can see that, sorry, we'll go back over here, and I'll refresh code coverage. And we can see that we have executed this line of code. Now, why don't I go ahead and load up a different demo. I'll try this domino tower. So we'll go back to the Observatory main page, and now we can see that we have a new isolate for this tab. And I'll show you another feature in Observatory called the allocation profile. So at the top of the allocation profile, you have high-level information about both of your heaps, how big they are, how many collections have occurred, how frequent the collections are. And then underneath, we have a breakdown on a class-by-class basis of allocations. So we can see that the most allocated class in this program is double, which makes sense because it's a physics simulation, so you expect a lot of doubles and other floating point types. List, we can't conclude much because they're so common in Dart already.
Yeah, it's not a smoking gun.
No, but one byte string, this actually looks really strange. This is a physics simulation, and somehow we've allocated over 1 million strings, or a mega string.
A mega string.
Yeah. So why don't we, like this looks really weird, because after one byte string, we see float64 array, mint, vector2. These all make a lot of sense for what this program is doing. Something strange is happening, and why don't we try and figure out what's going on? So in order to figure out the rate that we're allocating one byte strings, I'm going to reset the accumulator, and this accumulator is a counter that I zero, and then we increment every time we allocate an instance of that class. So I'll reset the counter, switch back over to the demo, and let this run for, let's say, 5 seconds, and come back, and I'll refresh. So we can see in 5 seconds, we actually allocated almost 2 million new instances of string. This is really bizarre, and we need to figure out what's going on. So why don't we go over to the CPU profile and see if we see anything string-related that's hot. So we're looking at the CPU profile now, and we see these different categories like Dart, native, GC News Space. Dart is the category that's set when we're actually executing script code.
So Dart is the stuff you all write,
Yes,
basically.
exactly. Yeah. And so if we skim down here, I'm looking for something string-related. We see stuff around vector2, calling sign and coast. This all fits. And down here at about 1.76%, we see string, one byte string concat all. So something is doing string concatenation, but we don't know what yet. So if I expand this, we can see who's triggering the string concatenation. And we see that string concatenation is being triggered by string base interpolate. So
we're seeing the callers here as we open it up?
Exactly.
Okay.
Yeah. So interpolate calls concat, and the canvas rendering context set fill color and set stroke color RGB call string base interpolate. None of this is my code. Canvas rendering context 2D is part of Dart HTML, but underneath this we can see canvas draw set color. This is actually part of the Box 2D demo harness. So what I'm going to do is I'm going to open this up in another tab, and we can look at what the source code for this function does. Now this function gets a color as a vector, and it passes in the vector contents for red, green, blue, and then passes in a hard-coded alpha value.
It looks innocent.
Yeah, I don't see any string interpolation going on here at all, or really have any intuition as to why we would be doing that. So why don't we actually dig in and look at the Dart HTML implementation of this function, which, because we're running Observatory and we have access to all source code, we can actually take a look at this. And we see the smoking gun right away. We see that even though we're passing in the color as integers, immediately a string is interpolated of RGBA, and then this string is passed off to the DOM. So even though we've gone to all of this trouble to keep the color as integers, every single time we set it on the canvas, we're indirectly allocating a string, or in our case, 2 strings.
Mm-hmm.
So why don't we see if we can fix this? And just like a cooking show, I am going to put
It's ready
something
to
in
come out of the
oven.
oven.
Yeah, and then I'll go ahead and load up.
In fact,
my
what do you
turkey
call
here.
this project?
This is the turkey project. The
Yeah,
turkey
good.
is done and it's fixed.
Yeah.
So let's see. So I'll go back to Domino Tower,
Sort of
bring
like-
up Observatory again, and I'm going to hop over to the allocation profile. I'm going to come down here. I'm going to reset the accumulator again, and I'm going to let this run for about 5 seconds. I'm going to come back over here, and I'm going to refresh. And we can see that one byte string has now fallen way down. It's now only 1,000 strings are allocated in every 5 seconds versus 2 million. So this is a drastic reduction in GC pressure and allocations.
It could be worse.
Yeah, it could be a lot worse. But now let's go back over to the CPU profile and see if we can see this one byte string function as being hot. And I don't see it. We'll just 1 byte. Nope,
I think that all the calls were from that thing. So
Yeah.
all the string interpolation you've probably removed at this point.
Yeah, I think so.
That's 1.5% you
Yeah, so
pulled out on the benchmark.
1.5% faster of running this benchmark demo, and we're allocating a lot less memory. So all in all, a net win.
Mm-hmm.
Let's go back to the slides. All right, so what did we just see? Well, you saw me browsing through the running program, looking at live code coverage. I was able to inspect specific instances, locate instances of class that I was interested in, invoke code on a running instance. We looked at the allocation profile, which has per class statistics, and user and per heaps garbage space information as well. We used the user controllable accumulator to figure out how many strings we're actually allocating. And then we used the CPU profile to go and find the smoking gun that was actually triggering all of these string allocations. So now I'm going to turn it over to Todd, who's going to give you a debugger demo.
Okay, so the debugger is sort of a fresh feature in Observatory, very recently added, all done in 2015. And I'm going to show you the debugger finding a bug in an actual program. Now, this program is one that I wrote with my kids. Where is it? Oh, there it is. My kids, I want to teach them programming, so the family trade. So we're writing a text adventure game. So this will be the second game demo you've seen today, significantly more low tech. So you're in a mysterious chamber. There's an exit to the west, a deadly mousetrap lies nearby. For those of you who aren't familiar, a text adventure game, you type in commands like take mousetrap, and then you're holding a mousetrap, and you can take your inventory and you're holding one. And you can walk around. You can go, oh, here's a rust revolver, so I'll take the revolver. I'll go south. Now, there's a bug in this program, which is my kids want you to be able to fire the revolver and to have something delightful happen in the game. So let's try to shoot the revolver. It says it's too rusty to shoot. That's not the bug yet. So I'll take the oil can. I'll oil the revolver. And now I'll shoot it. And boy, will be amazed. No, it's still too rusty to shoot. Here's our bug. We will use the Observatory to find this bug in our program. So let's go over to the browser and bring up Observatory. So here we are back at that initial page where we show all the isolates. I'm just going to hop straight to the debugger. And what you're seeing here is a split window. The top will display the frames, and the bottom is a console that has some input and output. You can type commands much as you can in GDB. Like if I type help, it lists all the commands that are available right now. It has standard stuff like setting and removing breakpoints, printing expressions, continuing, pausing. It's basically what you would expect in a command line debugger. So let's set a break at main, and I have tab completion here, so I'll hit tab there.
So this tab completion works for
functions, so like main, but also for scripts. So I'll do main.dart.
Nice.
Line 92, which I happen to know is the code that's going to handle the shoot command. So I'll set that breakpoint, and then I'll come back over here and shoot the revolver again. And it's frozen, which is good, right? That's a breakpoint. So we come back over to the debugger, and we can see that we actually have frames up here. And I can expand and contract frames. Each frame, when I expand it, shows me sort of a cutout of the code. It shows me a current position. It also shows me off to the side local variables that I can expand and inspect. But let's look at our top frame here. We are at line 92, and let's print an expression like player. So player is the object that holds all information about a player. Let's show some browsing. So here's a player. It has a current room. The player has an inventory with 3 items. Let's see what I'm carrying. I'm carrying a mousetrap. I'm carrying a revolver, and I'm carrying an oil can. So this all agrees with what I've seen so far in the program. Going back to the debugger, let's single step. So I'm going to hit end a single step. I'll hit return to do the next command.
One of the coolest things here, and it might not be obvious because of the font size, but you actually see the blue cursor move column by column. Mm-hmm. So you see exactly what part of the code is going to execute next.
Yeah,
nice.
That change was actually within the same line.
Yep.
So yeah, that little blue box there, that's what you're looking for. And here we have the item. Let's see what item it is we're about to shoot. It is the revolver. And looking below, we see that it has a field called can shoot, which is currently false. This is going to be the cause of our bug, but let's just pretend we don't know that yet. We step. If the item.canShoot is true, it's going to do something. Oh, it skips it. OK, so the revolver is still too rusty to shoot. Let's continue, go back and shoot it again. This time, we're going to use Observatory to modify the data as we go and actually explore the branch that we intended it to go down. So step, step, up arrow. I have command line history. Let's print the item.canShoot is false. Now I'm going to set it to true. And continue. And now it should be the big surprise. Success. The revolver backfires and we die. Welcome to my children. So let's go back to the presentation here. That's sort of a taste of the debugger. I didn't show you some of the isolate management features. We have the ability to switch isolates from within the debugger and to rename isolates so that if you've got a bunch of them, you can give one of them a distinguished name and know what it is you're doing. A second feature it has that DevTools doesn't is the protocol supports multiple clients. So John can be running a debugger and I can be running a debugger on the same exact VM at the same time. When I step through the program, he'll see the program state change.
Yeah. It's really awesome to see it live. Maybe later today, if you stop us, we'll give you a demo in person.
Yeah. That was a little bit too much of a high wire act for up here.
Yeah.
But it's also nice maybe at work and home you can have a connection there. So next page. Now we're going to talk about when we're adding features to the observatory, what it is we think about as we're designing features. The first is that we should always be collecting information. The VM knows a lot about your program. It has your script. It has your source. It has parsed it. It's turned it into classes and functions. It's compiled those functions. And then it's run those functions. All of these things, it knows exactly what's happening all the time. It also knows the heap. And because it's garbage collected, it knows where every single object is in your program. And you should have all this information available to you while it's running in real time. I mean, there's no excuse for every VM in the world not to provide this information to you all the time. In addition to that, we have a sampling profiler. It's low overhead and always on. So when you connect up to the VM, it's already got the profile sitting there, and you can already figure out what it's been up to. All right, second point. The observatory is self-hosting, meaning it's built into the Dart VM. When you open up the port, it'll serve it out. So it's always available. Observatory is like the turtle. It carries its shell on its back. It's always home.
So another design principle we have is that we want you to be able to observe the running program. There's a lot of great tools out there that require you to start your program with a special flag or run it in a special harness. And this makes it really difficult to diagnose real-world problems that you only encounter in production. So even if you forget to run with the command line flag that enables the observatory HTTP server, you can just send your process on the server the sig quit signal, and that's going to trigger the HTTP server to be activated, and then you can connect. And since we've always been collecting the information, we have all of the historical information. You can actually dig in and diagnose what's happened after the fact without needing to run in a special environment. It really helps you diagnose problems in the wild.
So manipulating the running program. You saw John call set as edge and change the coverage information as he went. I changed the can shoot property of the revolver and made it backfire. But in a real world scenario, you could do something like turn on logging. You've forgotten to enable logging. You want to see the logging messages. You connect up to the observatory. You tell it to evaluate logger.enable in the top level root library evaluation area. And then suddenly you've got logging output coming out of your program without restarting it.
Nice. So we've kind of mentioned this already, but we wanted to support from day one the idea that Observatory and the service protocol is a multi-user collaborative experience. So when you have every page in Observatory has a unique URL. So when you have this URL and you go through the necessary port forwarding steps to forward from localhost to your external address, I can take this URL, I could chat it to Todd. Todd could then paste it into his browser, and he's looking at the exact same page in Observatory that I am. In the running program.
So to reiterate, when you start this up, it starts on localhost.
Yes.
Yeah.
Yeah.
And
So
you
we
have to
bind a
forward the
local
port if you
host,
want to share
and
it.
if you want to share something externally, you have to go through the necessary steps on your operating system to forward the port. But if you go through those steps, then you could even chat. You could send a link to somewhere on the other side of the world and debug together. So finally, we want to build an ecosystem for tools. So every single thing that you see in Observatory, every interaction we do with your running program, happens over the VM service protocol. And this service protocol is available to anyone, allowing you to create custom tools that extract just that piece of information you care about. And we're also working with IDEs to do deeper IDE integration, where the IDE communicates over the service protocol and serves up interesting information. An example is internally we have a code coverage tool that, after all running the unit tests in the Google source base, then exports the code coverage out to this shared dashboard. And it gets that information off of the service protocol.
To that end, pretty soon we're going to be publishing draft 1 of the service protocol. We're still tidying it up right now, but the details of this protocol are that it uses something like JSON RPC, so the requests and responses are JSON, and it uses WebSockets. It should be pretty familiar to people.
Yep. So take a look out for Dart Announce. We'll have an announcement in the next coming weeks.
So what have we been doing? Since the last time we gave a presentation on Observatory, some of the new features have been the debugger, which we've shown you before. That's pretty fresh. Additionally, I want to talk about annotated script view. There's a person on our team, Ryan Macknack, and he says that the more information you can associate with the program source, the more understandable it is for people, because you're showing them like runtime information associated with the stuff they actually wrote. And so we're trying to provide more and more script annotations in the program. And John showed you this with call site information. He clicked on that one constructor, and it was able to show us the actual constructor that got invoked at that line of code.
Both the class and the method.
Both the class and the method.
So kind of furthering that point of tying things back to the source code that you wrote, the CPU profiler now understands function inlining. So in the past, if you looked at the profile, you might see one function that kind of had globbed up and inlined lots and lots of other functions that your program is executing. That made sense to compiler engineers and people on the VM team. It was obvious what was going on. But for a regular Dart developer who doesn't understand the ins and outs of the compiler, it can sometimes be confusing. So now the profiler understands inlining and will expand it out so you see the call stack that makes sense to you, the author of the program. We also have metrics. So user programs can now provide counters and gauges. And Observatory can connect and sample these things and show you a live counter. Like, for example, a server might have how many clients are connected to me right now. And you can go in and watch a graph, like a dashboard in Observatory.
OK. So what's coming next? We're going to improve debugging quite a bit. Right now, we have some weakness around developer workflow. Specifically, I edit my program and I want to restart. I have to actually reconnect to the Observatory. It would be nice if within Observatory you could support VM restarts or even individual isolate restarts. That would be a nice addition, and we're going to work on that. Additionally, you saw in my demo, I was switching back and forth to standard out to look at my output from my program. There's no reason that standard out and other streams shouldn't be broadcast within the console in the debugger window. In fact, it'd be nice to be able to say, when this feature completes, let me know in the debugging console and have it print that out too.
Yeah, that would be great. So we want to have a timeline view. So right now, the profiler is a statistical average of where your program's spending time, but sometimes you need to pinpoint a specific time range. So we're going to add a timeline view that indicates things like when method compilations occur or when a garbage collection occurs, and let you see how that interacts with your running program. We also want to be able to answer the question of where do I allocate class foo, and only class foo.
Yeah, just class foo.
No. We want to give you allocation call sites for any class in your program so you can narrow in.
All right. Last, as we were saying before, we want to display runtime information alongside the source, using the source as a model for exploration of this stuff in a way that's understandable. So the source code should be live, hyperlinked view into all of this information that we have that so far hasn't been shared with the user.
Yeah, I can't wait until I can hover over a variable and see its value.
Or its guard class, or whether it's nullable, or whatever.
Yeah, anything that we can collect at runtime.
Yeah.
So where can you use Observatory? Well, we've already said this many times, but Observatory is available everywhere where the VM is. So you can use it for server, command line applications, for developing Sky applications, which you'll hear about tomorrow. Any web applications running in Dartium, Observatory is available there. And we're also integrating with IDEs like Sublime, Dart Editor, and WebStorm so that there's buttons to launch and connect to Observatory for the running program. Finally, Observatory is a suite of development tools bundled with the VM. That means you already have it. Everyone here has this. So please try it out and send us bug and feature feedback. We really want to make sure that this is useful to everyone. And the best way we can do that is to hear from you.
Yeah, we want to make this the tool that you use to write your server-side Dart code.
Yeah. So on the slide, you can see Daniel and Ryan, two other members of the Dart team that help us with Observatory. So feel free to grab any of us if you want to talk about Observatory later on today and tomorrow. Thanks.